In today's lecture, we will discuss macrostate and microstate. Actually, the concept of macrostate and microstate is very important in the study of statistical mechanics. Whenever you will study the classical statistics or quantum statistics, always we need the idea of macrostate and microstate. So today's lecture is very important. This is a very important fundamental fact, and after knowing this concept, the study of statistical physics will be very easy to you. So be serious, watch the video seriously, and I hope after watching this video, your concept about the macrostate and microstate will be very clear. Actually, I am going to explain the macrostate and microstate by a simple example. As you know, this idea of macrostate and microstate is needed for the study of both classical statistics and quantum statistics. But my this lecture is limited to explain the concept of macrostate and microstate only for classical statistics. When we will talk about the quantum statistics in the forthcoming lecture, then we will again see this concept. This concept will be actually then extended to quantum mechanical system. But in the present lecture, we are uh, just limited to our discussion for the classical statistics. When you talk about the classical statistics for a system, you know that a system is actually composed of a large number of particles, okay, that may be atoms, molecules, or any other particle, okay. And in classical statistics, we simply consider that the particles of the system are identical but distinguishable. It means when we study the classical system, we assume that our particles of the system may be are actually distinct, and that's why we can label the particle, we can name the particle like A, B, C, D, and so on. Okay. As you know that the spin is purely a quantum mechanical property of particle. So when we talk about the classical statistics, we never think about the spin of particle, because this spin of particle plays a very important role in distribution of the particle in different quantum states. But in case of classical statistics, as we do not take into account the idea of a spin, because spin is associated only with the quantum mechanical system. So here never think about the spin while you are going to discuss the distribution of particle in different phase cells, okay, or in different compartments. And when this spin is taken under account, then we will study in quantum statistics that there will be two classes of particles known as bosons and fermions, and actually the distribution of fermions in different energy states or in different quantum states is restricted by a very famous principle which is called Pauli's exclusion principle. But as a spin is not needed in the discussion of classical system, so we also never think about the Pauli's exclusion principle. So the restriction imposed by the Pauli's exclusion principle on distribution of particles is not applicable in case of the particles of a classical system. Okay. And as I have told you that we will explain the concept of macrostate and microstate by taking a very simple example. Actually, when we will take a very simple example and we will talk about these two concepts in terms of that simple example, the concept will be very clear to you. So now let us start to know what is this macro state of a system. Okay. Let us consider a problem. There is a system of particles and we have to distribute those particles in the different compartments, or you can say that in different phase cells of a phase space. This is our basic problem. So in how many ways we can distribute the given number of particles in different phase cells, this is the basic problem regarding this macrostate. And to explain it, as I have told you, we will consider a very simple example. So for develop the idea of macrostate, let us consider there are four distinct particles or four distinguishable particles. Okay, so number of particles we consider very small for simplicity, although in general the number of particles in a classical system is very large. But to develop the idea of macrostate in a convenient manner, in a simple manner, we consider a simple system consisting of four particles. And as this system is a classical system, so you can say that according to the assumption of classical statistics, these particles are distinguishable, and so we can name those particles. So let us consider that four particles which we have assumed are A, B, C and D, and at any moment you can actually identify that that particular particle is either A or B or C or D. Okay, and the number of phase cells or the number of compartments we also consider very small. For simplicity, we consider there are two compartments or two phase cells, or in other words you can suppose that there is an open box, as I have shown in this figure. This is just an open box, and this box has actually two compartments which I have marked here by the number 1 and 2. This 1 and 2 represents the two compartments, and let us consider that these four particles will be thrown from any place so that any particle will fall either in the compartment 1 or in the compartment 2. Okay, and both of these compartments, or in terms of classical statistics you can say both of these phase cells, are entirely identical, exactly identical you can say. Since both the compartments or phase cells are exactly alike, the particles have the same priori probability of going into either of them. Or in other words, you can say that the probability of particles falling into any compartment is 1 by 2, because the particle will fall either in compartment 1 or in compartment 2, so that events will be actually, the actual number of events taking place will be 1, but 2 events may take place. So the probability of falling of particle in a compartment will be simply equal to 1 by 2. Okay, this probability is actually known prior to the event, and so this is actually called priori probability. Okay, now the possible number of ways in which these four particles can be distributed in these two compartments will be what? You can think that we can consider that in compartment 1 there is no particle and all the four particles are in compartment 2. This may be one of the arrangement. In second arrangement, you can consider that one of the particle is in compartment 1 and the remaining 3 is in compartment 2. So this is the second arrangement. In third arrangement, you may take that there are 2 particles in compartment number 1 and 2 particles in compartment number 2. So this is the third arrangement. Okay. In the similar manner, we also assume that in first compartment there are 3 particles and in the second compartment there is one particle. And in a fifth manner, you can consider that all the 4 particles are in compartment 1 and there is no particle in compartment number 2. So as a whole, you can see that there may be 5 arrangements of distributing these 4 particles into these 2 compartments or these 2 phase cells. Actually, I have shown this distribution in tabular form. From this table you can understand this distribution. Here see the table that I have marked here. This one, this is actually the number of compartment or the number of phase cell. So this 1 represents the first phase cell or first compartment, and this 2 actually represent the second compartment or the second cell. As I have told you just now that if in distribution number 1 we can consider that there is no particle in first compartment and all the particles are in the second compartment. So this is one of the arrangement. The first arrangement is 0, 4. Okay. In second distribution, you have considered that there is 1 particle in compartment number 1 and 3 in 2. So this is another distinct distribution of particle. This is marked by 1, 3. Okay. And in a similar manner, in the third distribution, we considered that there are 2 particles in compartment 1 and 2 particles in compartment 2. So this is your third arrangement. In fourth arrangement, we considered that there are 3 particles in the first cell and the 1 particle in the second cell. And in the fifth arrangement, you consider that all the 4 particles are in compartment number 1 and there is no particle in compartment 2. So as a whole, you can say that these are the 5 distinct arrangements. So if the number of particles is 4 and the number of compartments will be 2, in that example, the number of distinct ways of arranging these particles in these 2 compartments or 2 phase cells will be simply 5. Okay. Actually, this cell-wise or the compartment-wise distribution of particles is called macrostate. So all these arrangements represent a macrostate. This 0, 4 is one of the macrostate, 1, 3 is another macrostate, 2, 2 is third macrostate, 3, 1 is fourth macrostate, and 4, 0 is fifth macrostate. So I have mentioned here, you can see that for a system, so each compartment wise or phase cell wise distribution of particles is called macrostate. Okay. Now if we now consider that there are n particles instead of 4, we in general consider there are n particles, but even then we consider that there are 2 phase cells or the 2 compartments, and we have to distribute all these n particles which are distinguishable among these 2 phase cells or these 2 compartments. Then what will be the number of macrostates? You will see that the number of macrostates will be n plus 1. As in this example, when the total number of particle was 4, you can see that the total number of macrostates is 5. All these represents a macrostate. So the total number of macrostates, when you consider the number of particle 4 and number of compartments 2, then the number of arrangements, compartment by arrangements, or you can say the number of macrostate is 5. So if there are n particles and all these n particles are to be distributed among the 2 phase cells or 2 compartments, then the number of macrostates will be n plus 1. And what will be those macrostates? You can say the first macrostate will be 0n. it means there is no particle in first compartment and all n particles are in second compartment. The another macrostate will be 1 and n minus 1. Third one will be 2 n minus 2. Okay, and similar manner the nth n plus 1th arrangement will be n0. Okay, so in this case, if the number of compartments is restricted to 2 but the number of particles in general is n, then the total number of macrostates is n plus 1. And what are those macrostates? You can see these are 0, n, 1 minus 1, n minus 1, 2, n minus 2 and so on. Okay. So in fact, as I have told you that each compartment wise or phase cell wise distribution of particles is known as macrostate. Okay. So you can say that this 0n is a macrostate, 1n minus 1 is another macrostate, and this is actually, you can say, the first macrostate, this is the second macrostate, and this will be actually the n plus 1th macrostate. Okay. So I hope from this example you have definitely understand what is a macrostate. Okay. As I have told you, we will clarify the idea by a simple example, and this was a very simple example because we have actually considered the number of compartments 2. So this was the discussion becomes very simple. But when we will actually solve the actual problem, or we will study the classical statistics in the forthcoming lectures, then there will be not only 2 compartments, there will be a large number of compartments. But generalizing this idea, we can find the number of macrostates and what are those macrostates in that examples. Okay. So after knowing about the macrostate, now our aim is to clarify the concept of microstate. Okay. In fact, in the example which I have just illustrated, you have seen that the particles are distinguishable. Okay. And so that each compartment wise distribution can have a number of different distributions. Okay. Because the particles are distinguishable. And when you consider the each distinct arrangement for a given macrostate, there will be distinct arrangement of particles because the particles are distinguishable. Okay. So the each distinct arrangement of corresponding to a macrostate is called microstate of that macrostate. What I am actually telling you, this will be actually clear to you. So let us see here. You have learnt just now that if there are 4 distinguishable particles A, B, C and D, and we have to distribute them into the 2 compartments marked by 1 and 2, then what was actually the possible number of macrostates and what was those macrostates you have already learned. Now we are going to see that how many distinct arrangements is possible corresponding to a given macrostate, and that number of possible arrangement corresponding to a macrostate is called microstate. Okay. So let us see. See this table. This all things will be clear to you by this table. I have shown here that this is your first macrostate 04. Okay. And when you consider that your macrostate is 04, it means in compartment number 1, there is no particle. So I have written here 0. All the 4 particles A, B, C and D are present in the second compartment. So this is only one arrangement which it will be possible for this macrostate 04. Okay. And as the number of possible distinct arrangement for this macrostate is only one, which is 0 and ABCD, so the number of microstates corresponding to this macrostate 04 is equal to 1. This is the number of microstates. But now let us see the another macrostate. Another macrostate is what? This is 1, 3. Okay, you have learned. When you say 1, 3, it means there is only one particle in compartment 1 and the remaining 3 are in compartment 2. But as the particles are distinct, so we can consider any one in compartment 1 and the remaining in 3. So if you consider that particle A is in compartment 1, then the remaining 3 particles B, C, D will be in compartment 2, and this is a distinct arrangement. We have considered that A is in compartment 1 and B, C, D are in compartment 2. But if you consider that particle B is in compartment 1, then the remaining particle A, C, D will be in another compartment, and this arrangement is different from the previous arrangement. That is the arrangement A and B, C, D, and B and A, C, D both are different because particles are distinguishable. Okay. And we can also consider that in compartment 1 there is particle C, and in compartment 2 is ABD, and in the fourth manner you can consider that particle D is in compartment 1 and the remaining particle A, B, C are in compartment 2. So you can see that corresponding to this macrostate 1 and 3, there are 4 distinct arrangements. All these arrangements A, B, C, D, B, A, C, D, C, A, B, D, and D, A, B, C. All these 4 arrangements are different. And as I have told you that the total number of distinct arrangements corresponding to a macrostate is the number of microstates. So the number of microstates corresponding to this macrostate is what? This is 4. I think you have understand. And if you have understand, you can see the other examples and you can tell what will happen. See here. Now we consider the third macrostate of that example. This is 2, 2. When you say 2, 2, what does it mean? It means in first compartment there are 2 particles and in second compartment also there are 2 particles. But what will be that pair of particles? Since the particles are distinguishable, so we can take the different pairs. So let us in first set, let us consider that the particles A and B are in compartment 1 and the remaining C and D are in compartment 2. This is a distinct arrangement. Okay. Now we consider that particle A and C are in 1 and B and D are in compartment 2. Similarly, you can take that particles A and D are in compartment 1 and B and C are in compartment 2. Okay. Or at the place of compartment you may also say phase cell. Okay. And in similar manner we can consider that the particles B and C are in compartment 1 and remaining A and D in compartment 2. Okay. And similar manner you can take B and D are in compartment 1 and A and C are in compartment 2. And finally you can take that C and D are in compartment 1 and A and B are in compartment number 2. Actually if you will further think that there will be some more arrangement, you will find there will be not any further arrangement after this. So you can see all these 6 arrangements are distinct. All these 6 arrangements are different from one another. You can't say that the arrangement AB and this CDAB are identical because the particles are distinct. So when in compartment 1 the particles are C and D and in another is A and B, and when you consider that in compartment 1 particles are A and B and in compartment 2 these are C and D. These are different from one another. So you can see corresponding to this macrostate 2, there are 6 distinct arrangement of the particles. Okay, and as the number of distinct arrangement corresponding to a macrostate is called microstate, so for this macrostate the number of microstates will be what? This will be simply 6. Okay, and in the similar manner you can see that if we consider the macrostate 3, then we will have to place or put 3 particles in compartment 1 and 1 in particle 2, 1 in compartment 2. And so let us put the particle A in compartment 2, then the remaining B, C, D will be in 1. Now place B in compartment 2, then remaining A, C, D will be in 1. Now if C is in compartment 2, then remaining A, B, D will be in 1. And when D is in compartment 2, the remaining A, B, C is in 1. So for this macrostate again we find that the number of distinct arrangement of particles among the 2 compartments are actually 4. So the number of microstates you can say is 4. And in similar manner for the macrostate 40, you will have to put all the 4 particles A, B, C, D in compartment 1, and there will be no particle in compartment 2. And so corresponding to this macrostate there will be only 1 arrangement, and so the number of microstates for this macrostate is 1. Okay, so I think you have understand how this microstate is different from the macrostate. In nutshell, you can say that when you talk about macrostate, that is simply the number of arrangement of particles in compartments or in phase cells. But when we take into account what will be the distinct arrangement of particles among these phase cells, that represents the microstates. Now in this condition, what is the total number of microstates you can easily see. The total number of microstates from this example you can see this will be 1 plus 4 plus 6 plus 4 plus 1, that is 16. And this 16 can be written as 2 to the power 4. Why I have written 2 to the power 4, you can understand actually this is a general result. If you consider that here actually this 2 represents the number of compartments or the phase cells, and this index 4 represents the number of particles. Okay, so in general if you consider that there are G number of compartments, G represents the number of compartments or number of phase cells, and N represents the total number of distinguishable particles, then for that system the total number of microstates will be G to the power N. G to the power N. For example, if you consider that there are 3 phase cells or 3 compartments, and N is equal to, let us say 3. N is equal to also 3. Then what will be the total number of microstates? That will be 3 to the power 3, and that will be 27. Okay. So in this way, remember this result, that if G represents the number of compartments or number of phase cells, and N is the total number of particles which are distinguishable, then the total number of microstates will be equal to G to the power N. Total number means the sum of the number of microstates corresponding to the different macrostates. Okay, different macrostates. So I think from this simple explanation, by taking simple example, definitely the idea of macrostate and microstate have been clear to you. Okay. Now we will see another concept which is actually regarding the thermodynamic probability, or you may also say it thermodynamic frequency. Okay, thermodynamic probability or thermodynamic frequency. Actually, this thermodynamic probability is what? This is nothing. This is simply the number of microstates corresponding to any given macrostate. As you have seen in this example, that corresponding to this macrostate, let us say 2, 2. Sorry, the page has been turned, but this will be just okay. So see here, the macrostate which I have considered is 2, 2, and you can see corresponding to this macrostate 2, 2, the number of microstate is what? This is 6. In simple manner, this number of microstates which is 6 for the macrostate which is 2, 2, this 6 is called actually the thermodynamic probability or thermodynamic frequency of this macrostate. Okay. So if I will ask you that what is this 4? This 4 is the number of microstates corresponding to the macrostate 3, 1. So if I will ask you that what is the thermodynamic probability of the macrostate 3, 1? What is the thermodynamic probability of macrostate 3, 1 or thermodynamic frequency of macrostate 3, 1? Your answer will be what? Your answer will be 4, because thermodynamic probabilities simply represents the number of microstates corresponding to a given macrostate. Okay, so there is no difference between the number of microstates and the number and the thermodynamic probability or frequency for a given macrostate. Okay, so I have mentioned it here. You can see that the number of microstates corresponding to any given macrostate is called thermodynamic probability or frequency. Okay. Now, what will be actually the thermodynamic probability or frequency? You can see actually when you say that this is just equal to number of microstates corresponding to a given macrostate, actually the microstates represents the meaningful arrangements, mark it, meaningful arrangements or meaningful permutations of various particles in the macrostate, excluding the meaningless permutations. There may be meaningless permutations when, for example, if you consider that there is a particle and that will be replaced and another identical particle will acquire that position, then there will be no creation of new state. So if you count the number of states or number of microstates in that condition, taking that permutation 2, that will be wrong. That is called meaningless permutation. So excluding the meaningless permutation, the number of meaningful permutations or the number of meaningful ways of distribution of particles, that is actually called the thermodynamic probability. Okay. Now we will again formulate this idea by a simple example. For this, let us consider the total number of particles in our classical system is equal to n. But here again, to clarify the concept in a simple manner, we restrict ourselves to the for the number of phase cells or number of compartments at 2. I have considered that there is only 2 phase cells or only 2 compartments for simplicity. Okay, but the number of particles in the system is n. Okay, it means these n particles are to be distributed among the 2 cells. This is cell number, let us say 1, and this is 2. So if you consider that N1 is the number of particle in first cell and N2 is the number of particle in second cell. When you say N2, that means the remaining number of particles, and remaining number will be what? That will be N minus N1. So that N2 will be simply equal to N minus N1. Okay. So you can say that among these two cells, N1 is the number of particles in first cell, and N2, which is equal to N minus N1, that is the number of particles in second phase cell or second compartment. In fact, in that condition, you have definitely studied the permutation and combination in your course on algebra, and definitely you have an idea of it, that the number of meaningful arrangement in this condition will be what? That will be simply NCN1, or you can also say NCN2. Value of NCN1 and NCN2 are same. You have definitely an idea of this. And when you say NC1, NCN1, that means what? That is n factorial divided by n1 factorial times n2 factorial. And instead of this n2 factorial, you can write n minus n1 factorial. Or instead of this this n1 factorial, you can write n minus n2 factorial and n2 factorial. Okay. So the number of meaningful arrangement of n particles among the two phase cells or among the two compartments will be simply equal to NCN1 or NCN2, and which is equal to this much. Okay. But as I have told you that the number of meaningful arrangement of particles among the phase cells represents actually the number of microstates, or you can say the thermodynamic probability. So the thermodynamic probability in this case will be simply equal to NCN1 or NCN2. So I have mentioned it here. You can see the number of microstates in the macrostates N1, N2, or the thermodynamic frequency or probability. This will be what? This is actually equal to, if we denote this probability by the symbol W, that W is equal to NCN1 or NCN2, and that will be equal to n factorial divided by n1 factorial times n2 factorial. Okay. You can check this formula, because we have already calculated the number of microstates corresponding to a given macrostate in our previous example. You can see. So as you have considered 4 particles distributed among the two phase cells or two compartments, the first macrostate was 0, 4. So now let us find the number of microstates or the thermodynamic probability for this macrostate from this formula. Let us try to find. You know that the thermodynamic probability W, or the number of microstates, will be what? Because formula is NCN1. Here N means 4 and N1 is 0. So this is 4C0. Or NCN2. N2 is 4. So this is 4C4. And what will be this? This will be 4 factorial divided by 0 factorial times 4 factorial. You know 0 factorial is what? This is equal to 1. So this 4 factorial and 4 factorial will cancel, and this comes out 1. So what is the number of microstates or the thermodynamic probability corresponding to the macrostate 0, 4? You can see this is 1. And the same thing you have seen earlier in this example in tabular form. I have already mentioned. You can see this for this macrostate 0, 4, the number of microstate is 1. Okay. So that formula is correct. You can check. Okay. Now let us take the another example. This is the macrostate 1, 3. Okay. So here N1 is equal to 1 and N2 is equal to 3. So you can write it, and the total number of particles N is equal to 4. So you can write this thermodynamic probability will be equal to 4C1 or 4C3. This is NCN1 or NCN2. And that will be simply equal to 4 factorial divided by 1 factorial times 3 factorial. Now 4 factorial you can write this is equal to 4 times 3 factorial. And 1 factorial you know is equal to 1. So I have not written it here, and 3 factorial. So this 3 factorial and 3 factorial will cancel and your result is 4. Okay. And you have seen earlier that for this macrostate the number of macrostate is 4. So the formula is checked. Okay. And in the similar manner, now try to find the number of microstates or thermodynamic probability for this macrostate 2, 2. Here actually N1 is equal to 2 and N2 is also equal to 2. Okay. So from that formula W is equal to 4C2 and that will be 4 factorial over 2 factorial times 2 factorial. Now 4 factorial you may write 4 into 3 into 2 factorial. And 2 factorial is simply equal to 2 into 1, that is 2, and this is 2 factorial. This 2 factorial and 2 factorial will cancel. This is 2 times 2, so 2 times 3 is equal to 6. And that's why you can say that the thermodynamic probability or the number of microstates corresponding to this macrostate 2, 2 is equal to what? This is 6. Okay. So from these examples, definitely you have a concrete idea of the macrostate and microstate. It is just a deep belief in you. Have you understand or not? Actually, when you follow a textbook, the idea of macrostate and microstates are written in vague, and so the students, most of the students get confused. But I think from this video, which is very simple to understand the concept of microstate and macrostate, this concept of macrostate and microstate will be definitely very clear to you, and the manner you will find very convenient to understand this idea. And so watch the video seriously and write your comment in comment box, and if you have any problem or any doubt you may write in comment box. I will try to solve your problem or solve your doubt. Okay, thank you very much.